Hello and welcome to our mini podcast series that we are recording because there's going to be an amazing conference in Luxembourg called Physics for Future. And one of the reasons our guest is with us today is that he is coming to Luxembourg very soon. And I hope you will have a chance to see him live. If I got you interested already without knowing what the guest is, it's on the 14th and 15th of May. And our guest today is Professor William D. Phillips, who is an American physicist at the National Institute of Standards and Technology, NIST. In 1997, along with Stephen Chu and Claude Cohen-Tanuji, he won the Nobel Prize in Physics for his contributions to laser cooling. Bill, thank you so much for coming today to talk to us.
It's a pleasure to be here.
Something that you do pretty often, which is talking to youngsters. When you are sitting in front of a crowd of younger people, and one of them asks you, what do physicists do? What is your answer?
Well, one answer is that physicists play with really cool toys all day. At least that's what experimental physicists do. That usually resonates with kids of a certain age. And it's true.
That is true, although you have to be very careful with your funding agencies, right? Because if you start talking about cool toys, they're not very excited.
Well, that's an interesting point. One time I was invited to give a talk at a military research laboratory. And the person who was in charge of research there specifically asked me to come because she thought that the style of my talk would encourage her researchers to play around. And she felt that that was an important feature in doing research, to have a spirit of playing around, because that's how you make real progress. If you just keep doing the same things that you know how to do, well, you'll get better at doing that. But if you just play around, you may discover new directions that will be more useful than the things you've been doing. So she wanted to encourage that among her researchers. I work for a mission agency. Our mission has to do with providing standards of measurement that will help industry do its job, produce better products to make people's lives better. There are other funding agencies. I mean, we're not really a funding agency, but we're a research agency. There are other funding agencies like the National Science Foundation, whose job is to explore new things. So they may not say playing around exactly, but that's what their job is to fund people to do new things, to explore research directions that people haven't been exploring before.
In other words, do fundamental science.
Exactly. I remember when I was a lot younger, there was a general idea that we should avoid what was called at that time curiosity-driven research. But I think that today people understand that curiosity-driven research is exactly the thing that produces real progress.
And this is exactly what you try to also tell the youngsters, don't you, right? Keep your curiosity.
Indeed, that's my usual advice when people ask, what is your advice to a young person who's interested in science? And that advice is, stay curious.
What do you think why we don't? Because this is one of really the big questions I always ask myself. I'm so curious in all my interviews, whoever is the scientist, especially when I'm preparing, I spend hours and hours reading. Not everyone is like that. So you keep it, you are innately like that as a child, but then it goes away.
Exactly. I think that all children start out curious. Why that changes, well, I'm not really competent to answer that question because I haven't done or studied the research that people do. I don't even know whether people have done research in that, but I can make some guesses. When you go to school, it's necessary for the people who are teaching you to maintain a certain degree of order in the classroom. And that kind of order is antithetical to the kind of unbounded curiosity that young children have. So, for example, when I go into a kindergarten class, one of the things that I do is I pour liquid nitrogen on the floor. And what happens is that every child in the classroom is immediately out of their seat and on the floor wanting to see what is this wonderful stuff that is boiling as it hits the floor. Well, that kind of behavior is not conducive to an orderly classroom. And if you did that and encouraged that all the time, it would be very difficult to teach students the other kinds of things that they have to learn. So I think that a good teacher somehow maintains a balance between encouraging the natural curiosity of students and maintaining some degree of order that allows them to operate a classroom.
Let's move from children to an adult setting. I'm sure it happens to you that you're at a dinner party and you end up next to a person who is not very excited about sitting next to a physicist. And then when they ask you what you do, I guess you don't talk about expensive toys.
Well, let's say that we've already gotten through the part that I am a physicist. What do you do as a physicist? My simple answer, what you might call the elevator story of what I do, is we make the coldest stuff in the universe. We make things that are colder than anything has ever been. And that sometimes will encourage someone's curiosity.
Sometimes.
Yeah. And then the question is, why? Why do you do that? How do you do that? What does it even mean to be colder than anything has ever been?
I feel a bit bad to be a typical journalist and yet again ask you to talk about the Nobel Prize and what is laser cooling. But let's have it out of the door and then we can talk about physics for future.
Okay. So it's actually easier to talk about why if we first start with what. Let's begin with what does it mean to be hot or what does it mean to be cold? Let's talk about a gas, like the air in the rooms in which we're sitting. The air is made up of atoms and molecules, mostly nitrogen. And those molecules are moving around. The faster they're moving, the hotter the temperature of the gas. In fact, temperature is simply a different way of measuring what the energy of motion of the atoms and molecules in the air is. So when we talk about cooling a gas, which is what we do in my laboratory, it means that we're making the atoms and molecules, usually it's atoms in a gas, the atoms move more slowly. Now, why do we want them to move more slowly? And the answer is we can measure them better. You can well imagine that if something is moving at the speed of sound, it's not so easy to measure it. It's in your field of view and gone in a tiny fraction of a second. That makes it hard to measure things. The main original motivation for doing this, for cooling down a gas, was to make better atomic clocks. Clocks are things that tick, and the best tickers are atoms. All kinds of things can change the ticking rate of a clock. Think of a pendulum clock, a tall clock, or what is sometimes called a grandfather's clock. The pendulum swings back and forth. Galileo discovered that the period of a pendulum hardly depends on how far it swings, and that made it a good choice for a ticker for a clock. And the Dutchman Huygens made clocks based on this. But if the length of the pendulum changes with temperature or humidity, then that's going to change the ticking rate. And that's true for almost all tickers. I'm wearing a quartz watch, and the temperature can change the ticking rate of that quartz watch. Well, atoms also tick, or at least tick in a certain sense. They have energy levels, and the energy difference between those energy levels corresponds to a frequency. That is, if I want to make an atom make a transition from one energy level to another, I can shine in radio waves or microwaves or laser light, depending upon how far apart the energy levels are. And the frequency of those waves is a ticker that I can use to make a clock.
Now, I just wanted to say that this is one of the things that you are going to present as well in Luxembourg, right?
Indeed.
So if people want to see the pendulum or to see some other discussions of clocks, that's exactly, as I said, 14th, yes, in Tramschapp in Luxembourg.
Yes.
You can hear Bill talking about time, Einstein, and the coolest stuff in the universe. Exactly. And now you can go on.
Well, and so in my talk, for example, to illustrate what I've just shown you, I'll have a ball on the end of a string and have it swing back and forth, and I'll show that if I change the length, then the period of the swinging changes. Well, atoms also, in the sense that I've described, can be thought of as being tickers, and they are very little affected by anything. The background temperature changes their ticking rate a little bit, so we control that. If there's light on, for example, that can change the ticking rate, so we carefully control that. So it's really relatively easy to make atoms immune to changes in their ticking frequency much more easily than any of the kind of mechanical clocks that we're used to thinking about. But if those atoms are moving through our apparatus really fast, there's all sorts of things that come from having the atoms go so fast. The limited time we get to measure them is one of the most important things. But there are other things, Doppler shifts. So a lot of people are familiar with the Doppler shift. Every wave phenomenon can experience a Doppler shift. One of my favorite examples, maybe it's not so good for Luxembourg, but let's imagine you're on the seashore and you see waves coming in and you count how many waves come in a certain interval of time. That tells you what the frequency of the waves is. Now, if you were to get into a boat and go into the waves would hit the front of your boat at a higher frequency than they're hitting the shore. And if you were to turn the boat around and head back toward the shore, then the waves would hit the back of your boat at a lower frequency than they're hitting the shore. Well, the same thing happens with light, with sound, with any kind of wave phenomena. So if I have atoms that are moving around and I'm trying to see what is the right frequency to make a change from one energy level to another, that frequency will appear to the atom to be higher or lower, depending upon whether the atom is moving toward the source of light or away from the source of light. And since the atoms have a whole range of different velocities and they're going in all different directions, this is a mess. And so I want to stop that from happening. And the way I stop it from happening is make the atoms go really, really slow. And once I have them going really, really slowly, I can also make things even better by trapping them. So now they can't go very far. And that, if I do it the right way, can almost eliminate this problem of the Doppler shift. So that's one thing. Another thing, and one of the reasons why Einstein's name comes up in the title of the talk that I'll give, is that Einstein taught us that time itself is relative, meaning it depends on who is measuring the time. Moving clocks appear to run more slowly to people who are, say, at rest in the laboratory. This leads to what some people call the twin paradox, because the moving person looking at people in the laboratory thinks their clocks are running slow. And so if they come back together, who's older and who's younger, since each one thinks the other one's clock was running slower? Well, we could talk about that. There's a simple answer to that, but it's really an interesting concept to think about. That concept, which we sometimes call the twin paradox, affects the operation of atomic clocks. And these atomic clocks are so accurate that this effect, even though it's quite small, is a big influence on the precision of these atomic clocks. So that's another reason why we want to have the atoms moving more slowly, because we get rid of this Einstein effect, this relativistic effect on the clocks. And we've done very well at that. When I first moved to the National Institute of Standards and Technology in 1978, at that time it was called the National Bureau of Standards, the best clocks, which were our clocks, the National Bureau of Standards clocks, were good to about a part in 10 to the 13. Now that sounds incredible. That's a part in 10 million million. And you think, why does anybody need a clock that good? Well, there's lots of good reasons, which we could talk about.
Well, that's exactly my question, actually, if I may, because I was thinking, I mean, sure. I understand. I don't want to be the devil's advocate, but I would actually ask you, why do we need to measure it so precisely?
Yeah. Well, there's a number of reasons, both scientific and practical. If we didn't have clocks that good, we never would have been able to build the satellite navigation system. So this satellite navigation system, which is built into all of our mobile phones, is dependent upon atomic clocks that are in satellites orbiting the Earth and broadcasting information about what time it is on the satellite, and also broadcasting information about where the satellite is. And that's determined by using clocks that are on the ground, looking at the clocks that are in orbit, and figuring out from all that information where the satellite is. And you see, if you then know how far away you are from 3 different things, and you know where those things are, you know where you are. Sort of, we might call that triangulation. And that's what the GPS or the satellite navigation system does. It sees how far you are away from at least 4 different satellites. Because since your mobile phone doesn't have a clock in it, it has to get that information from having an extra satellite. So if you had a good clock in your phone, and we're working on that, maybe in a few more years, you'll be able to have a really good clock in your phone, and that's going to make the whole thing work even better. But now we get that extra information by having more satellites.
Why can't you have an atomic clock in your mobile phone yet?
Well, the atomic clocks of the sort that I'm talking about, the ones that we have on the ground, typically have a room full of electronics and optics. But we are working on making atomic clocks that the size of the physics part of it, not necessarily all the electronics, is the size of a grain of rice. Now, we still have to add some electronics and some lasers and things like that, but we know how to make those things miniature as well. And so we're working toward making these things so they could go into a mobile phone. They are now available as mobile units, not quite small enough to go in a mobile phone, and maybe not quite cheap enough to go in a mobile phone, but people are working on that.
Okay, and then we don't need the satellites.
Well, we still need the satellites. It's just you don't need as many. And everything works better and works quicker if you've got your own clock. But that's one of the reasons why we want to have good atomic clocks. Now, the atomic clocks that are in space are not laser-cooled, not yet. But the ones on the ground that are looking at the satellites that are in space are laser-cooled. And so that makes their quality so high that we don't have to worry about how good they are. So it just makes everything easier if you've got really good clocks. So that's a practical reason why you want to have good clocks. There are other reasons having to do with communications that work better if you've got really good clocks. Now, there are scientific reasons why you want to have really good clocks. There are certain constants of nature that determine what the world is like. One of those constants is called the fine structure constant. It's a constant of nature that essentially tells us how strong electromagnetic forces are. Now, electromagnetic forces are the forces that determine almost everything about our lives, the way chemistry works, the way materials behave, almost everything about our ordinary existence other than gravity is determined by electrical forces. Now, there are nuclear forces that determine how nuclei work, but while it's really important that the nuclei work in the way that they do, we don't really experience it on a daily basis. But electromagnetic forces are really important. Now, the question that often arises is that constant, the fine structure constant, that determines how things in our ordinary experience behave, is that actually a constant? Does it change from year to year? Well, with really good clocks, we could make 2 different clocks that depend upon the fine structure constant in different ways. And then we can compare them over a long period of time and see if the ratio of their ticking frequencies changes. And because of laser cooling and other advances in how good clocks are, we now know that from one year to the next, that constant does not change by 1 part in 10 to the 18. Now, 1 part in 10 to the 18 is a billion billion. It's a part in a billion billion. That would correspond to a clock gaining or losing less than 1 second in the age of the universe. So it's a really, really fine number. And we now know that thanks to these better clocks. We now know that to that incredible accuracy. But we'd like to do even better. For example, we'd like to have those 2 clocks and then move them together in a gravitational field and see whether that changes their ratio. Einstein's theory of gravity, we call general relativity, says it should not. But what if it does? Well, that might give us a clue as to there being something wrong with Einstein's theory of gravity, which is annoyingly correct, because we've got a real problem. We don't know how to make a theory that encompasses both Einstein's theory of gravity and the theory of quantum mechanics that describes how atoms and molecules work. And that's really upsetting that we can't join these 2 theories, which describe their different domains very, very well. You'd think you could have one theory that encompassed them all, and Nobody knows how to do that. But if there's something wrong with one of those theories, then that might give us a clue as to how we could proceed. And so that's another really scientific application that having really good clocks gives us.
It's great that you mentioned quantum mechanics and quantum physics, because that was also my question, because we're talking about measuring, right? And we know that measuring, maybe you shouldn't, because then you just influence everything, right? Or should you?
Well, you have to. If you want to get information, you must measure. But as you say, making measurements influences what's going on. What we do with atomic clocks, it's all about quantum mechanics. And what you've described is the idea that the act of measurement disturbs the system, and this leads to what's often called the uncertainty principle. The fact that when you measure something, you cannot measure two complementary variables perfectly at the same time. Now, what does this have to do with atomic clocks? Well, for atomic clocks, those two complementary variables are frequency and time. Now, frequency is what we want to measure with the clock. Time has to do with how long we get to measure it. So if we take a very long time to measure it, then it means that we haven't specified when in that time interval we're looking at the clock. We're looking at it over that whole time interval. The longer that time interval is, the better we can measure the frequency, because it's the product of the two uncertainties that can never be smaller than a certain number, which in the case of time and frequency, that number is, 1 or 1 over 2 pi or something like that. For position and momentum, that number is Planck's constant. This is why, or another way of saying why, we want the atoms to be going so slowly, because it means we get to measure them for a really long time. So if we can make that time interval long, therefore, in a sense, making the uncertainty in the time really big, it allows us to make the uncertainty in the frequency really small. And that's what we want for a clock, or at least for a clock that does the kinds of things that we've been talking about.
Okay, so that's the atomic clocks. But I know that from the laser cooling that you've done a couple of years ago, you're developing also other things and looking into other things. So, looking into the future right now, before I actually ask you a little bit about the past. But first, let's start with the future. What do you think, like in 10 years' time, it's like a job interview question. Like, what do you see yourself? But I also want to say, where do you see physics in 10 years' time?
Sure. Well, one of the ways I would answer that in a job interview, depending on what the job is for, and I think it's a good answer for physics as well, if I knew what I was going to be doing in 10 years, I wouldn't be doing the right thing.
Very true. Yeah.
But that doesn't mean we don't dream about what we might be able to do in 10 years. So one of the things that I'm sure you and your listeners have heard about that's really exciting these days is the possibility of quantum computers. And it turns out that laser cooling is one of the developments that has made certain kinds of quantum computers possible. So quantum computing, for those who haven't been following this, is the idea that you store and process information not as binary bits the way we do in our ordinary computers and mobile phones and a whole panoply of digital devices, not as binary ones and zeros, but as what we call qubits, quantum bits, where the information is stored, for example, in an atom, in what state the atom is in. One of our favorite states is the spin state of an electron in an atom. Take an atom like rubidium that has one unpaired electron, one valence electron, as your listeners may have learned in high school. And that valence electron, of course, I'm using my hands now, but this is probably all audio. But imagine my thumbs pointing on the two hands pointing in the same direction. If I flip one of them over, that's a different energy state. And I could use those two states where the spins of the electron and the spin of the nucleus are pointing in the same direction, and when they're pointing in opposite directions, as two different states. And I'll call one of them 1, I'll call the other one 0. So it's just like binary information, except the difference is, and this is the thing that's so wonderful and also so strange, that this qubit can be both 1 and 0 at the same time. And that's the thing that is so strange about quantum mechanics, is that things can be, in a very real sense, in two places at the same time, in two states at the same time. Now, when it comes to information, this sounds like it's going to be a disaster, because when a qubit is in such a superposition, it means that if I look at it to see which state it's in, I'll get one answer or the other. but I have no idea what that answer will be if it's in what we call a superposition of being in both states at the same time. Now, I should say that this description of the atom being in both states at the same time is a little bit too cavalier for an accurate description of what is going on. But the fact is that nobody really understands what it means for something to be in a superposition. It's something that is outside of our ordinary experience. And so it's not really possible to give a good, understandable explanation of what it means to be in a quantum mechanical superposition state. I can tell you what the results of the measurements will be, or at least what the statistical results of the measurement will be on things that are in these superposition states. But what's really happening? Well, that's not such an easy thing to do. A lot of physicists would say it's not even a valid question. The idea of reality, the only real thing that there is the result of a measurement. The idea of what is the state really doing before I measure it? A lot of people would say that's not a meaningful question. Reality doesn't exist until we measure it. It sounds like this is a disaster when it comes to doing information processing because you don't know anything. But it turns out that for certain kinds of problems, there are what we call algorithms, procedures we can follow with the quantum computer that will produce wonderful results, that will allow us to calculate things in a relatively short period of time that an ordinary computer, what we call a classical computer that uses ordinary binary bits, would take an inordinate amount of time to calculate. And that gain in speed, in functionality of a quantum computer has got a lot of people excited. Now, it isn't going to make everything better, but it's going to make certain kinds of calculations, especially calculations having to do with quantum mechanics. It's going to make those calculations better. And maybe that'll result in some wonderful things, being able to design new kinds of materials, or new kinds of drugs, or new kinds of energy harvesting hardware. We don't know yet. Those kinds of things are still in the future. I think it's still accurate to say that no quantum computer has yet calculated anything that anybody cares about faster than a classical computer has. But I think we're getting really close.
But I'm not following one thing. You said cooling the atoms in quantum computers, but like, how do you cool something if you don't know where it is?
Yeah, right. We can know approximately where the atom is. And now the uncertainty principle comes into play. If we know approximately where it is, we have some uncertainty in its position. That means that there's a certain minimum uncertainty in its momentum. So what we'd like to do is to make that uncertainty as small as we can. Because when we do processing using these atoms, we want to minimize the uncertainties in where they are and how fast they're going, because they will make the processing uncertain. And we want the processing to be as certain as possible. So this is one of the reasons why cooling and trapping, I haven't really talked about trapping very much, but that's confining an atom to a particular location. This is one of the reasons why cooling and trapping is so important for doing quantum processing with atoms, is that we do need to know where the atoms are. We do need to know how fast they're going, or at least what state they're in order to know what the operations that we do on the atoms, what the results of those operations will be. So that's one of the reasons why cooling and trapping has been an important enabler for certain kinds of quantum information. It gave us atoms in the kind of condition that allows us to use them as quantum bits, things that we can have very good control over. You can well imagine that if your atom is whizzing through your apparatus in thousandths of a second, that's not a very good situation for trying to make that atom do exactly what you want it to do. But instead, if you've got it held in a laser beam that confines it to a distance a lot less than a micron, a millionth of a meter, and has its temperature down to a millionth of a degree above absolute zero, this atom is going to be good for doing quantum information processing.
I made you jump to the future, right? And I'm sure that there will be loads of different paths you could also name. We could continue talking about it, but I also wanted to now go back to the past and just looking back at all the years. What do you think in fundamental research in general? What have been the most important advances for you? Of course, quantum, in general, developments in quantum, we can say that for sure. What else? Or is it that the thing?
Let me just continue with that for just one moment about quantum. A few years ago, I was asked to participate in a panel discussion in which a number of physicists were asked the question, what was the most important physics development of the 20th century? Now, you might think this is a hard thing to answer because there are so many things that we learned in the 20th century. We learned about both special and general relativity. We learned that there are things outside our own galaxy. Think about that. I'm not sure whether it was actually within the 20th century that we learned that there are planets around almost every star. Amazing things. But almost everyone on that panel said the most important thing was quantum mechanics.
So you do agree?
Absolutely. And why? Because quantum mechanics not only changed the way we think about reality, the fact that we no longer have a clear picture of what is the state of something before we measure it. That's a rather fundamental change in the way we think about the nature of the world. But quantum mechanics has changed our daily lives, has changed the daily lives of almost everyone on Earth. It is quantum mechanics that makes electronics possible. Only because we've understood the quantum mechanics of the way electrons move through solids has it been possible to have semiconductor electronics. And semiconductor electronics dominate what we see as being modern technology. Without semiconductor electronics, our lives would be fundamentally different. Now, you could argue whether the changes have been good or bad, but they've certainly been huge. What other amazing things have happened? Well, I mentioned a few of them. When I think about it, the idea that there's stuff beyond our galaxy, the fact that we did not know that at the beginning of the 20th century. But here's another thing which is related to quantum mechanics. At the beginning of the 20th century, a lot of people did not believe that matter was made up of atoms and molecules. Now, that is mind-blowing, that within the lifetime of people that our parents knew, I knew very well that people didn't believe that matter was made up of atoms and molecules. The famous, iconic physicist Richard Feynman said that if you imagined that all scientific knowledge were lost and you had to restart everything, but you could pass along one piece of information to future people to help them to reestablish our understanding of science, he thought that piece of information would be that matter is made of atoms and molecules. That is the most fundamental thing for understanding how things really work. And the fact that it was really Einstein's understanding of Brownian motion and the subsequent experiments that happened after that that finally convinced people that stuff is made up of atoms and molecules. Plenty of people, of course, believed it. People like Boltzmann, people like Maxwell believed this, but it was not generally believed by even the scientific community, let alone people at large. So that's a huge development in the 20th century. I could go on with details about, it's really a further development of quantum mechanics, but quantum electrodynamics, the fact that the vacuum is not empty. So this was a concept that was developed in the early part of the 20th century, but its effects were really only felt toward the end of the 20th century. The fact that the vacuum is actually a sea of changing electromagnetic fields, and in a certain sense also a sea of particles popping in and out of existence, and that we can see the effects of that. Not only see the effects in scientific experiments, but also have them dominate the observation of things like gravity waves. So it's by playing with those effects of electromagnetic fields that exist in the vacuum that we have been able to improve the performance of gravity wave detectors. And there's another thing, gravity waves. So gravity waves were predicted based on Einstein's theory of gravity early in the 20th century. And now in the 21st century, we're seeing them. But only because of all of the advances of the 20th century has it been possible to make these gravity wave observatories like LIGO and Virgo. And the thing that I find amazing is that these devices have not just confirmed, yes, there are gravity waves, that they've taught us new things about the way the universe works. It seems like every time another bunch of gravity waves come along, we get a new insight into how things work. The fact that a large part of the heavy elements in the universe have been made by the collisions of black holes. That's amazing.
I totally agree. As probably listeners can hear, this is a discussion of two extremely curious people. So, of course, I mean, this is all absolutely mind-blowing. But just to wrap up, because unfortunately we have to wrap up, going back to the beginning of our discussion. So, school children. I was just wondering, so of course what Richard Feynman said, I totally agree with. I probably would pass on that message as well. And this is the message we do pass on to school children. So that's in the educational system for sure. But quantum, not necessarily, right? I mean, some basics, yes. But do you think it's because in general, youngsters, let's call them like that, don't have the tools? Or because we also know that adults don't get it, but in general, is it because of the tools, or is there something we should change as well to equip next generations?
Well, I think it's both. On the one hand, it is rather hard to understand at least the details of quantum mechanics if you don't have a certain mathematical background. At the same time, I think that we can convey, maybe not to kindergartners, but we can convey to high school students the excitement and the wonder of quantum mechanics. There are people who are saying we should start teaching quantum mechanics to children in kindergarten. I don't agree with that. My boss said that someone told her we should instill all this sense of wonder and strangeness in these kindergartners about quantum mechanics. And she said, my daughter still believes in the tooth fairy. I don't think that quantum mechanics is going to impress her all that much. But I think that what we need to do with kindergartners is share with them the excitement and the wonder of science itself. And then as they grow older, they will be more receptive to learning more and more about science. And the more they learn, I hope, the more excited they will become. And when they learn about quantum mechanics, they'll have the tools to understand why it is so exciting and wonderful.
And this is really perfect to finish our discussion like this. And I hope that we all convinced you that it's absolutely worth going to the conference. Physics for Future will be trying to rekindle your excitement about science, about physics. So maybe you're already there. So you're already a physicist. So keep it going, because that's also important, right? In the academia, not always so easy to be always excited.
And it's going to be a lot of fun.
Exactly.
I'm going to blow stuff up, and I'm going to levitate stuff, and it's...
And remember that Bill is not the only distinguished guest that is going to be there. There are also other renowned physicists coming, so please check it out. There is a registration on the university website. And what remains is just to thank you, Bill, so much for today.
It's been a pleasure.
Physics for Future is organized by the Department of Physics and Materials Science at FSTM of the University of Luxembourg. Come join us on the 14th and 15th of May in Luxembourg. More information in the show notes.